Hello everyone, and welcome into yet another live stream. You can only hear me in one of your ears right now, and that was certainly planned. That was what was meant to happen. And the reason why you can hear me only in one of your ears is because right now you can in fact hear me in both with a slight echo, which I imagine is very annoying. So hello everyone, and welcome into yet another live stream, the second child checkpoint. Do let me know if the sound is fine, because I'm using both microphones at the same time, which was expected. This is planned. This is all very planned. Hi there, everyone. Hi there, Adrian. Hi there, Katsi. Hi there, Timon. Hi there, Lycan. Hi there, Flame. Oh, Flame. I haven't seen you in such a long time. Hi there, hi there, hi. All matter as well. Hi and welcome, hi and welcome. And I suppose without any further ado, we should begin with what the stream will be about. The sound is decent. Okay, well, I will take that then. Because today's live stream will be about something special, something very specific, and that is rotations. It is the Pi Day, after all, and I suppose that is what we should tackle. We would like to talk about rotations in a mathematical sense, but at the same time, physical interpretations are nice. Eventually, hopefully, building up to something very real, something very experimental, something NMR-ish. And so, as such, I suppose we should start with the physics, because physics is reasonable. You know, stuff like your angular momentums, your classical mechanics, your quantum mechanics. Quantum is tricky. Quantum, I don't actually know enough to present all by myself. I would need the help of someone. Who do I know who knows quantum mechanics? You could just walk over to the thing now.
It's my turn.
Yeah, just...
Let me just walk over then.
Come here. How about the beautiful? Now we know what to do with the second mic.
Apparently I am expert in quantum mechanics.
Yes! Today we will be giving you a lecture about angular momentum and spin in quantum mechanics. And if you have been following any of my live streams, videos, Discord, basically anything, then you know for a fact how much I like spin. How intuitive I think it is of a concept, and how easy it is to explain famously. So I imagine this will be no bother at all, and we'll do it very, very easily. If there was a convenient Remco in your closet. Yeah. So, let's start.
Let's begin. Let's commence.
And everyone's just saying hi to you. So I suppose we can begin.
Hello back.
I suppose we can start with something simple, momentum. I think that's reasonable.
That's reasonable indeed.
This should be fine.
Should I give the playground to you for a bit, or?
I can start with momentum. Momentum is pretty trivial. So, what is momentum? Can someone answer me what is momentum? Well, I will not wait for an answer because it's a bit too basic of a topic to actually wait for an answer. Momentum is basically the measure of how much movement your object can give, right? So if your object has a lot of momentum, that means it can cause a lot of movement. If your object has little momentum, that means it can cause a little bit of movement. It is basically it is closely related to kinetic energy, as you can guess. And so let's for a second think about what could actually cause your object to give a lot of movement or a little bit of movement. So we have two squares because I don't feel like drawing cubes. I just realized this is going to be absolutely tiny, but it picture squares in your head if you can't follow on screen. We have two of them, and let's say that we want the bottom one to be able to give a lot more movement than the top one. What could cause that? Well, the first thing is velocity, obviously. That's movement by itself, which means that if the bottom one has higher velocity than the top one, then the bottom one can cause a lot more movement simply by the sheer fact that it's moving a lot faster. This audio setup is cursed. It's like they could only afford one channel per mic. You know what? Fine. I said, and then it was fine. Fine, I said, and then it was fine. There we go. No. I said, okay, well. There we go. There. Happy now? Now it's better. Now we can't hear Remco. Well, it's me presenting. It's fine.
I have a question.
Yeah?
The bottom one is visible, but the top one isn't.
The top one isn't.
Yes, you have to make it a bit. Yeah, there we go.
Now it is. Okay, so first
Yes.
thing is obviously velocity, as we all know. But now let's say that we have our two boxes, two squares, two whatever dimension you'd like to pick, and the bottom one has higher velocity, but we still like the top one to give them more movement. Can we do that? Well, yes, we can. If the top one has a lot more mass, if the mass of the top one is actually greater than the mass of the bottom one, then despite having lower velocity, it has the possibility to have higher momentum. And so that's basically how you should think of momentum. You should think of momentum as the capacity to give movement. And right here, Remco, you can take over. Because now the obvious question would be, but what about angular?
Yes, what about momentum in rotations? Well, first, I need a pencil. Am I visible on the stream?
Yes, you very much are.
Perfect. So let's now consider instead of boxes, let's consider a particle going around a certain point. That is a circle. So, in other words, this particle is moving in with a fixed radius. In Cartesian coordinates, we would. Yeah, that one. We have our axes, x and y. Tell me if the ink is not visible, by the way.
It's barely.
Well,
they could not afford working markers either. Yeah, we
can go with red. Red is nicely visible.
I don't know if I can spill who we can blame for these improper markers. It's the British, obviously. They are to blame.
There we go. Red is visible. So, we have an object going around a certain fixed point. We want to describe a notion equivalent to momentum to that. Well, how are we going to do that? Normal momentum is given by the mass times velocity, or in fancier notation, the mass times the derivative of x dot. In angular momentum, we can do something similar. What we can do, first of all, is make a coordinate transformation. More specifically, we can define our coordinates in terms of radial and angle coordinates. Oh, it always trips me up which one I need. We can define x in terms of r and theta, and y in terms of r of theta. And basically what we're describing now is a certain... This would be our r component, and our theta component would be the angle, of course. When we're talking about an orbit, a particle orbiting a point, this would be at a fixed radius. So in other words, r does not change. So our velocity is purely in the angle direction. So one thing that we could postulate, or we could expect, is that our angular momentum, which I'm going to denote by L, is something of the form mass times this velocity in the angle coordinate. Now, when we want to go back to normal coordinates, x and y coordinates, this is a very simple exercise, which I will leave to the viewer. What you can do is, well, you can just take the time derivative of these, make sure r is not dependent on time, and do some algebraic manipulation. You get an expression looking like this. Where r squared is x squared plus y squared. So when we plug back this equation in our angular momentum, we get something of the form m times the velocity of y minus y times the velocity of x divided by r squared.
Yeah, and very interesting thing here, which needs to be accented, is this is the black one that works, right?
I would say the red one works best, but maybe the blue one works.
Well,
Yes.
We're here to experiment, except he isn't, he's a theoretical physicist. So the thing to accent here, which is very important, is that normally we have our momentum is equal to mv, right? Once again, everyone understands it. So you would expect that angular momentum would take the form something like m theta dot. Once again, if you have seen our videos, then you understand what theta dot means. Dot is just derivative in relation to time, just like v would be x dot, derivative in relation to time of this coordinate of rotation. So basically how quickly it's rotating. However, very counterintuitively, what we find instead is this. We have this division by r, which is a problem.
Perhaps we have some animations for this? Do they work?
If only had we prepared something that would work for this. Well,
Can you quickly make something?
I can try. Let me just see. I can open up Blender. You know what?
Takes like 2 minutes.
Very conveniently, actually. You know, this very fortunate timing. Because before the stream, I have put a massive screen behind. I just thought we could use it, so I put a comically large screen behind our whiteboards.
Happy Pi Day.
Onto which I can position Blender, and because Windows, there we are. Happy Pi Day, Happy Pi Day. And as such, what we could do, I suppose, I imagine, and I guess, is we could select our pipe, and we could consider an orbiting pipe. What would an orbiting pipe look like? Well, an orbiting pipe look like the orbiting pipe would have an orbit. It would have some kind of radius further away. And then what we can do is we can hide the other pipe for now, like so, and we can just let that sucker go. Wow, would you look at that? Isn't that impressive? Aren't you all glad that you all tuned into the live stream? You don't have that at home, do you? An orbiting pipe. However, very crucially, what is interesting is what happens when we add another pipe to the mix, our second pipe. Because now when we add our second pipe to the mix, and if we once again select it to only orbit, and we select the radius to be larger, then I would like you to notice what happens, because that right there is counterintuitive. There we go. Let me just make sure that their velocities are actually 0.5, I would say should be fine, and also the other one having velocity of 0.5. Despite them having exact same velocities, the outer pipe is traveling a lot faster. It's clearly visible, but if you don't believe me, I can pause for a second, and I can just zoom in on their velocities, and these green and red bars you see on the screen are the Cartesian velocities. And you can see that the outer pipe has just a higher velocity.
Yes. So what this means is that if we calculate the angular momentum of both of these pipes, perhaps you can put it on the screen, you would have to switch to the approximate one.
That is, yeah, I would have to switch to the approximate one.
Yeah, if possible.
So right here we have the approximate, our proportional momentums we have gotten earlier on, this one.
Yes, so if we were naively going with angular momentum being proportional to m times the radial velocity, then what we would see is angular momentum for both the pipes are the same. But this is unintuitive, because our second pipe has a way higher velocity. So we would expect it to have a higher angular momentum. And the way we resolve this is by rewriting by proposing a new form of our angular momentum where we get rid of this r squared dependence. So in particular, what we're going to define the angular momentum as is m r squared velocity of a radial coordinate. And if we do that,
then what we get is instead of an approximation, once again, I do realize it's taking a painfully long time, but you have to excuse me. I am blind on a good day, and this is just having to turn around, developing a hunchback. Honestly, the troubles I got, okay, that's enough talk. There we go. There, if we have our equality, it is all accounted for.
Yes.
Don't mind the inner outer pipe. They are
They're currently swapped.
They are currently swapped because we cannot keep track of our pipes, but the point still stands. Naively, you would think that it would just be proportional to m multiplied by angular velocity, because it would be just directly equivalent to classical momentum. But in reality, you need that term r squared to compensate for the fact that as you move away from the middle, the angular momentum actually increases.
Yes.
And I wonder if there's actually a maybe more intuitive way to think about that.
Well, perhaps we can rewrite one equation a little bit. Specifically,
we can actually do it another way. We can consider it as a vector, which I am one to do, considering how I like my graphics. So I suppose, if you wouldn't mind, I can. Oh, you know what? No, I changed my mind. You keep this one. I'm taking the blue one.
Perfect.
So, there we go. I am very pedantic about my pens. So, how would we consider this kind of angular momentum as a vector? Well, first of all, we'd have some kind of point around which we're going to be rotating. What next? Well, next we can imagine some kind of vector like so. That will be the point around the actual point that's rotating, or the actual object that's rotating, the position of that object, the radius away from the middle. Then what we consider is an application of some kind of momentum. Not angular momentum, just classical momentum, normal momentum. So let's say that we push it this way, because why not? It's a bit hard to see, but we're pushing it upwards. We're not aligning it perfectly with rotation, we're pushing it in some kind of random direction.
that is really hard to see.
It is really hard to see.
You might,
Well,
want to take that at one after all.
Yeah, that's fair. Well, then, also could you check me check it, oh, fine, we can do it, that's fine. Probably checking is good because I'm absolutely blind. All right, so once again, we have a point. We have our R, and we push it a certain direction, let's call it P. What's going to happen then? I would actually like to think, because the R cannot change. It's our object attached to a metal pole, it's on an orbit, it cannot change no matter what. Well, in that scenario, we can actually divide our P into two different vectors. So first of all, we can divide it going parallel to our R, and then we can divide it perpendicular, like so. And I am going to note them down as PU, which stands for P useless, and then PU, which stands for P useful. You cannot confuse the two, because if you confuse the two, that will ruin your equation completely, right? So it's important that you keep track of which one I'm talking about. And so in that scenario, what we can do first is we can absolutely disregard the PU. I called it useless for a reason. The reason why it's useless is because what is that momentum going to do? This is your rigid component. It cannot move. That's the constant radius. The radius will not change, which means the useless P just disappears. And all that we're left with is the useful P. Now, where do we take it from here? Well, ideally, we'd like to create some kind of map that takes our P and maps it onto PU, which is just a fancy way of saying we'd like to figure out what this vector is, which is surprisingly trivial. If you define your R as a linear function, then you can just define a second linear function, because you have the 2 points through which it's crossing, it's 0, 0, and it's Rx, Ry. Then your second also has 2 points. It's a little bit more tricky to see the 2 points because it's rather about the information. Doesn't matter. The point is then you get a distance between the two linear functions, which can be calculated, and the result you get is, if I am not screwing it up because I'm doing it from memory, Rx Py minus Ry Px divided by norm of R. If this is wrong, then that's an exercise for the user to figure out what should be the correct equation. It is correct, right?
I presume so. Maybe
X, Y.
Depends on what it's equal to.
Yeah, that's equal to the norm of the useful momentum. So this is, we have our momentum, we apply it. A certain part of that momentum disappears because it is fighting against the rigid constraint against which it cannot win. And all we're left with is the only part of momentum that makes it useful, and that's the part that actually rotates the object. That's the idea.
Thank you. So, with this conceptual understanding of momentum, angular momentum, we can now fill in the equations a bit. I'm immediately erasing the PUs. I did not consent to this.
It's P useless and P useful. How else would you note it down? The only reasonable way.
What we're now going to do is, first of all, we're going to rewrite this expression a little bit back into this form. So we now get the r squared cancels. We get m x y dot minus y x dot. And since we know that momentum is defined as, like for example, momentum in the x direction is defined as velocity in the x direction mx dot, which in this case we can substitute this in. What we get is x momentum in the y direction minus y momentum in the x direction. This is our final expression for our angular momentum in the xy plane.
You know what I just remembered? The thing I did with the vectors, the thing you erased.
Yeah.
I think there was an operation like that actually. The operation that did that. I don't remember what it is, but there was something in linear algebra that did that.
There might, I'm not
I don't
sure.
know. Just keep going.
Yeah, sure.
I'm just thinking about it.
Right. So now the next thing we can do, of course, is this was a two-dimensional rotation. We can also consider three-dimensional rotations. For example, we could consider a rotation in the YZ plane. Same thing, orbit around the origin is now in a different plane. Same thing for the ZY plane, or the ZX plane, I mean. What you do get is you get, for each of these planes, you get a similar value. You get an angular momentum with exactly the same expression, except your x, y, z, they become the corresponding values. So let me define this one as x, y, because it's in the xy plane. So that would be the same expression. If we look at the xz plane, what we get is xpz minus zpx. And similarly, the yz plane has ypz minus zpy. We're doing nothing fundamental here. We're just reusing the notations. But we can visualize it, what happens when we do the, the rotations in a different plane.
Yes.
It's one button.
Yeah. So right here we can have, as you can see, just our pipes rotating, because one must consider two pipes rotating, and then if we have them in a different plane, then that's it. You have no idea where the z-axis is. Oh, you think it's to the top. You don't know that. You don't know. I removed the z-axis. You don't know which way the z-axis is. Oh, you think the z-axis is to the top. What if I select all of it, and what if I do this then? What if I rotate? Now you don't know which way the z-axis is, but it's rotating the same way. Rotation doesn't matter on which axis it rotates. It has rotational symmetry by definition. So yeah, two-dimensional example of rotation is just three-dimensional rotation. That's just what it is.
Bold statement, we'll go through with it.
We're all working in standard spaces.
So, but now since we are in 3 dimensions, we have 3 different objects, or a certain orbital rotation in around some certain axis. What we can do is we can group them together. Because 3 objects, 3 dimensions, calls for a vector. So what we're going to define is we're going to define an angular momentum vector. And this is going to be defined as Lyz. Well, actually, I'm going to do first to the Lx. This has 3 components, Lx, Ly, Lz. And we are going to define these 3 components as Lyz, Lzx, and Yz. And the whole, if I plug this then in, it's once again a lot of writing for not a lot of intuition. I think this is it. You get a final vector which represents the angular momentum in 3 dimensions. Now, where do we go from here? Where do we go from here?
What's the
It would be nice if you knew
cross
it now.
product?
Cross
That was
product.
that was the operation I was talking about.
Elaborate.
Well, with the vectors, yeah. When you have, I knew it was something. Yeah, when
You
you
said
have
it.
when you have the point, this is dead. Well, happens. When you have a point, right, and then this, and then you have another vector, and then the separation into the useless, useful, right? This, the thing that I did, the thing giving you the norm. If you move the norm onto the other side, that would have actually been just the cross of the two. So actually, this would be just V cross P. I knew I just remembered. Yeah, you can get back to whatever it is you're doing. I don't
Thank
know what
you.
you were doing. I just.
Yeah, we'll go back with what we're doing by erasing the useless and the useful. This, of course, is the definition of the cross product. In this
Oh.
case, R cross P.
Wasn't that a coincidence?
So angular in momentum in 3 dimensions is nothing else than a cross product of your coordinates with your linear momentum. That is a useful result. So this we have now described angular momentum for an orbiting object, but there is a different type of rotation. For example, consider the Earth. Earth goes around the Sun. That is an orbital rotation, but the Earth also spins on its own axis. This is not an orbital rotation. So we have something for a solid object where if we move around its own axis, it also has some sort of rotation.
I would say this is way too small. I really wish we had like a visualization of this that we could put on like big screen.
You're right, it's way too small.
Yeah. Oh, I suppose that works. Yeah, so if we get back to considering our pipes, because if you take one thing away from this stream, it should be that all of physics can be solved if you just consider the pipes. So, if we get back to our pipes, you may notice that they are right now orbiting. This movement may feel unnatural, and you may have not noticed why. And the reason why it feels unnatural is because in both these scenarios, we have had the orbit, we have removed the spin part of it though. So if I go onto them and if I add the spin part, right now you will be able to see that they not only orbit, they also spin. I don't think there is a need to explain more the difference between the two because it's proved by you look at it and you can see it. You can see the pipes orbiting and spinning at the same time. They are two different kinds of rotations you can have. One does not necessarily mean the other, although really often we have both of them together.
Yes, so we would also like to discuss angular momentum for spin rotations. And in this case, we once again make an analogy with normal angular momentum. So more specifically, we have momentum equals mass times its velocity. And we are postulating that our spin angular momentum must be something of this kind. Mass in normal linear momentum acts as a kind of resistance to movement. The heavier a particle is, the more difficult it is to make it move. So we are going to say something similar. We are going to define it's called the moment of inertia. It is some resistance to rotation. It acts entirely analogous to mass. And then, of course, we also have the angular velocity right now. This would be the expression of the spin angular momentum. Now, in physics, it's usually very difficult to determine this one, because this one is very object dependent. For example, a sphere and a cube, they have different kind of moment of inertias. So,
if I am not mistaken, this because we consider the mass and the radius this time come together. So it would be the same exact equation as for the angular momentum. The only difference is that right now we have tracked the mass and the radius together, which means that if I made the pen, which means that if you have two different objects, even if they have equal mass, even if they spin at the same speed, this I will be screwy. Because if you have, we're just going to do two-dimensional because that's easy for now. If we have a circle, or filled in, and if we have a square, then even if they have the same density and the same mass, obviously the sizes here would need to change in order for that to be the case, then you can see that a square would have a different distribution. Circle would have a really even one. The square would have it at the corners where the radius is greater, or rather not the radius anymore, but the distance is greater than the distance to the side, which means that you actually need to account for it when it comes to the eye, and this makes the whole thing really annoying because you need to use synchros.
Yes. So you see the approach of finding spin angular momentum and linear or orbital angular momentum is different, but they are related in some way, because in defining a spin orbital of a spin angular momentum, what you need to do is circle, in case we consider the Earth, you need to define an axis of rotation. So basically, this Earth is spinning around this axis. Now, a funny thing that you can do is you can actually consider this axis outside of the body, which means it is now spinning around this axis, which means it is now orbiting, which means animation.
That is actually really curious, and once again, it's a bit difficult to see on its own. So I think...
Can you remove the equation?
Yeah, I feel like I'm going to very slightly take this. Definitely not because I just want you all to look at all matters out. I am very sneaky about this. And then what I'm going to do is just going to... There we go. There we go. All right, splendid. And now I can bring it back. And right now you...
It's...
Yeah, Windows sucks. I know. And right now you can see... Is this pipe spinning or is it orbiting? It's spinning. You can clearly see that it is spinning. However, if I go to the right, if I give you the axis around which it is spinning, represented here by this purple-violet bar, there we go. And then if I go up, if I increase or decrease the radius, you can see, let me just disable the orbit, or actually no, enable the orbit. You can see that it going away from the origin would turn this spin into a sort of orbit. It's not quite an orbit because it's still spinning, and it can actually be both. In what scenario would it be both?
Well, perhaps we can... I suppose we can define a pipe element, a pipe particle. Should we?
Define a pipe particle.
Define a pipe particle.
Pipe particle, for those who do not know, is obviously an excitation in the pipe field. We do have a whole paper in the works about that. We'll be releasing soon, publishing. We expect a Nobel Prize, at least nomination. So
when we are considering a point particle, things are a little bit different. A point particle.
Yes, as you can see, it's spinning. Or is it actually spinning? Is it spinning?
It looks like it's doing nothing.
It does look like it's doing nothing, but very curiously, if I switch back to the pipe, instead of the point, well, the pipe is clearly spinning, and all I'm doing is I'm just replacing a pipe with a point. So, shouldn't it be also spinning if I do it like this?
No, it shouldn't.
Well, yeah, because it doesn't really have anything to spin. It's a point. I mean, we're visualizing it as a sphere, but it's a singular point in space, zero-dimensional. So,
perhaps add the orbit for, I don't know, move the axis of rotation a bit out.
Oh, that's a good idea. We can move it a bit further away.
Yes.
Like this.
Yes. So what you now see is a point particle orbiting around some axis of rotation, and there is no spin. I suppose that's enough of animations.
Yeah, I guess that makes sense. I mean, how can a point spin? It's ridiculous. Let's not be crazy. It's a point. Can't spin.
Let's recap kind of what we talked about. In classical mechanics, we could have a pipe.
In classical mechanics, we could have a pipe is a sentence that can only happen on one of these streams, and I'm glad to be here for it.
We have a pipe that could either have angular momentum around a point, so orbital angular momentum. This is, of course, given by your cross product. And you could also have the pipe spinning on its own. This would be orbital. This would be spin. You could also have the pipe spinning on its own. It's the equation I just erased. Moment of inertia times the angular velocity. Now, if you consider a pipe particle that is infinitesimal, then your orbital angular momentum still exists. So you still have the same expression. Same expression, but your spin is not defined anymore. Because you're talking about a point particle, it has no structure to spin around. So this is just not defined. That is the main point we were trying to make in this first part of the stream.
Yes.
Is there any questions about this?
That is a good question. Is anyone confused about any of this? Because I will not lie, it is really crucial you understand all of this really well. Because if you won't, then it's going to get a bit too overwhelming. So
Yes, so I will repeat it one more time. Pipe has orbital and spin. Point particle has only orbital. The spin and orbital angular momentum are still related by moving the axis of spin outside of your body. So they're still kind of the same thing, but not for point particles. There is no such thing as spin for point particles.
okay, I think we're good with the question, because the only question that's been is, are we going to talk about spin-orbit coupling, which I feel like... So, so I think everyone understands pretty well, I would say, so far, the classical
You guys are
mechanics part.
ahead. Right. Classical, this is classical mechanics. Let's leave it in this corner.
That's because I know if you recall, but at the beginning of the stream, I did mention specifically that the whole point wasn't just to talk about angular momentum, it was to make it quantum.
Oh no, the board is doing the thing again. Magic.
Oh yeah, the place where we are has locally inverted gravity. It's just...
If you want an example of that.
Yes, let me just...
Okay, don't touch it anymore. I mean, to be fair, we just wanted another opportunity to show the Almetra art.
That is true. You know me so well.
Anyways, this is our expression for orbital angular momentum. We are now done with classical physics. We are now done with classical physics, which means there's only one thing to do, tiny step, quantum physics.
So first, just out of curiosity, and let me ask you all a question. If you had to turn this into quantum mechanics, turn this classical object into quantum mechanical one, how would you go about that? What would you do to it? I'm curious how much attention have you been paying to the recent videos and exercise sheets, which everyone, I'm certain, is familiar with. Timon says I'd put hats on it.
Okay, then let's try and do that. That's a good suggestion. So, quantum mechanics, angular momentum, orbital addition. Let's begin. Angular momentum is defined as the cross product. We now want to make this quantum. How do we quantize a vector?
Yeah, we have not really. If you recall, we motivated all of quantum mechanics by kind of expanding from...
I know how to quantize operator, position, hat, momentum.
You can think of it like, you take a single value to a matrix, basically. Well, matrix, it's a long story, watch the videos. But right now we're talking about a vector, right? It is an angular momentum vector because it has 3 directions.
Like this? Now there's too many things on top.
Hat of a vector, yeah. What do you think actually? Would hat come? I would imagine hat would come last because it's spiky.
Are you saying it's like this?
No, hat has to come last. Otherwise,
It has to be like this.
Yeah.
Surely. Anyways, shits and giggles aside, the way of quantizing angular momentum is not by looking at the vector itself, but looking at the components. So instead what we're doing is we had a vector Lx, Ly, Lz, and I suppose copy-paste?
If only.
Fill the space, I need to write something.
Well, in that scenario, I will say, hey, I hope I'm pronouncing your name correctly. I am really glad you're here. I really am glad. And we have also just uploaded a video, you can watch it after the stream, in which we talk about an exercise sheet on quantum mechanics. And if you would like, I would really be curious to see you complete this exercise sheet because you seem to be quite knowledgeable on the topic, considering the next question you ask is, does Lx, Ly, and Lz commute? Which shows a really good understanding of quantum mechanics. So I really, really, really appreciate that. No one else seems to be having any questions.
Well, they should have had questions because I made a mistake. This should be an X, this should be a Y, this should be a
Well, that's written in small text, so that's actually...
YX, this should be a Y.
Oh, you did write it ZY.
Yeah, I just messed up the entire thing. There we go. It
I
should
don't mean
be...
to be that... I could have just erased this in the middle. This is still XYZ.
Yeah,
Oh,
yeah,
no.
but no, like
Wait,
this,
no,
I
no,
messed up
that's
the
fair.
indices.
Oh, no, yeah,
Okay,
I see.
so once again, recap if you're working with this. X component of angular momentum means there is no X in the expression of...
Yes, the basic idea is that that's, well, if you want me to fill the space, I can fill the space with that, I suppose. Which is, what a perfect timing. How do you describe rotation? Rotation we won't cover on the stream. We're originally planning to make a whole separate live stream about rotation, but unfortunately we ran out of time because we had a lot of other things to do, which means I'm going to cover rotation in my videos. That live stream was supposed to be covered by me anyways, it doesn't matter. How do you actually describe rotation in 3 dimensions? Well, what you actually need is 2 things, which is first of all an axis around which you rotate, and the second of all the magnitude of your rotation, which is very conveniently happens to be described by a vector. Because if you imagine a vector as an arrow, which people who do linear algebra may not like, but they can piss off. But if you imagine a vector as an arrow, then you can actually imagine it as first of all very simple unit vector with a norm of 1, and then that multiplied by a scalar, which means that this can give you the axis of rotation, this can give you the amount of your rotation, which means that if you are considering a cross product to describe your rotations, the reason why you don't use the x in the x part of it is because we consider an axis we consider a plane on which the rotation is happening, like so. And then we consider the axis to be like this, which means that if it's happening on an xy plane, then the result would be on z. I think that should be listening understandable. There's going to be videos about this, so don't worry, but there we go.
Yes, so I will write the indices a bit bigger, sorry for that. But to quantize angular momentum, we are going to quantize all the components. So in particularly, the angular momentum in the x direction, we can quantize this, and this is then defined as y operator, p z operator, minus z operator, and py operator. Now, we can do this also for the other two. Will be a bit of writing. I won't need the filler for this one. So the momentum, angular momentum in the y direction is going to be quantized by z operator, momentum in the x direction, minus x operator momentum in the z direction. And similarly for the last one, angular momentum in z direction operator quantum blah blah is the x operator, which is the position operator in the x direction naturally, momentum operator on y minus y hat px.
I'm glad you're covering. My mask broke in the meantime, by the way. I'm very unfortunate, yeah. I have to do the rest without the mask on.
Happens to the best of us.
Yep.
I also lost my mask on many times. So, quantized. We have it quantized now. So, yeah, I suppose the hard work is done. Let's just see what we can do about this. There is one thing we can define. What we also could have done in the classical mechanics. Once you have a vector, you also can calculate the magnitude of your vector, which is just the component squared. This is just Pythagoras. We can do the same thing now. We can define a total momentum operator, L squared, which is going to be just the squared sum of all these operators. There we go. Let's just play a bit around. Indeed, let's listen to smart people in the comments, and let's just try and find a commutator. So more particularly, what we can do, since we know that our x hat with any other one that is called y hat, they commute, which means you can swap the order around. This is something we have seen before. It also follows from just calculating the Poisson brackets, then upgrading your Poisson brackets to commutators, which there is a great exercise about that. Similarly, for the momentum in x direction and momentum in y direction, for example, is also 0. And when we are talking about a x hat and a momentum x, then we actually do get a non-zero contribution, which is to say these two cannot be swapped around at zero cost. Since recall the commutator, of course, means in this case x hat y hat minus y hat x hat. So it's just checking the one way of multiplying with the other way of multiplying. And if this is 0, then that means if this is 0, that means that like x hat y hat equals y hat x hat, which means you can just anywhere you come across them, you can just swap them around. Doesn't hold for position and momentum. You will get an extra factor. Now, okay, pedantically, there should also be an identity operator here. Sure, you can forget that. What this means is that you cannot measure them simultaneously. In other words, when you measure position of your system, we all know there is the uncertainty principle. When you measure position, you cannot measure the momentum anymore. That is reflected into this commutator.
Chris also just asked x times y minus y times x, or is that a different operation? No, that is multiplication. A very crucial thing, though, is that unless I'm mistaken, specifically in fields, multiplication does not necessarily have to be commutative, which is very important. So, for example, consider matrices, the simplest one, or quaternions if you're feeling fancy, which are...
No, we're not feeling fancy today.
Well, we shall
but
see.
I had my fancy make it for her.
I mean, if we get a like a perturbation operator, then maybe we think fancy. But I doubt we're gonna get that. Come on, not operator, perturbation. What is it called? Epsilon, ijk.
Infinitesimal.
No, the.
Oh, the Levi-Civita.
Yeah.
Sure.
But I don't doubt we're gonna get that. That's so hyper specific.
No. So, let's just check one of these. Let's just check the commutator of these two. What this means is we're just trying to see if we can measure them at the same time. If we can measure the angular momentum in the x and in the y direction simultaneously. Is my audio still working? Because the thing fell off. I put it back on, but the thing fell off.
Well, if it's...
if it wasn't, then the
it
last...
is working.
Okay,
it's
good.
Working, okay.
Well, now let's begin. We have this expression. We need to plug this expression before the comma, this expression after the comma. Then we need to use the properties of commutators to write them in these three expressions. And exercise to the viewer, I am going to just fast forward to the solution, because I can do that. The solution is going to be I, h bar, angular momentum operator in the z direction.
That makes sense.
Which means they do not commute, which means you cannot measure them simultaneously, which means you need more than 2 eigenvalues for them. Differently said, it's not very nice. So let's instead look at something else. Let's instead look at this one, the momentum squared operator with, for example, LZ operator. We can pick any of the three. What this means is now you plug this in here, you plug this one in here, you need to use this identity, use the commutator properties, and you will find very easily this is 0. What this means is if we want to measure angular momentum in the z direction, we can also measure angular momentum as a total, like the total angular momentum. We can measure that, and we can simultaneously measure angular momentum in the z direction. In other words, what this means is that we have some state where if we try to measure our total angular momentum, we will get some certain value. Let's call it A. But also, on the same state, nothing changes, we can try and measure angular momentum in the z direction. We should get a different value, of course, but we should get a value nonetheless. This is an eigenvalue equation, too, for which, well, these are both true because of this commutator property, because of this commutator vanishing. Now, let's store this real quick. Let's try and work with that. So, how are we going to continue? I need to look in my notes real quick. I generally forgot how to continue from here.
Well, from here, the plus minus.
Yes, right.
I
So,
would imagine.
yeah, what we're going to define, we have used the LZ operator, and that means we still have two operators left. We can do something with these operators, and more specifically, I'm also going to erase the classical part. More specifically, what we can do is we can define an L plus as angular momentum in the x direction plus I complex number times angular momentum in the y direction, and also L minus, same thing with a minus sign. Now we can see how these two are acting on our states. And for this, we need to rewrite our states a little bit, because I don't think this doesn't look easy.
Yeah, no. I mean, I'll be brutally honest with you. I personally am gonna absolutely forget that, because the whole bit there is that your state psi can give you two different kinds of eigenvalues, which I personally am gonna forget. So if you could just like rewrite it as, I don't know, AB,
Fine.
I guess.
I'm going to rewrite my
that should work.
state a little bit easier, so that you can explicitly see the A and B dependence. So the A will be for the total angular momentum operator, and the B will be for the angular momentum in the z direction. There we go. Now we can see how our L plus and L minus are acting on these states. And for this, first thing you can note, I have already suggestively written them down with a plus and a minus. And yes, this is related to creation annihilation operators in quantum harmonic oscillator. So let's very briefly recap that.
Yeah.
We had some states, n. We've shown this twice, I believe. 3 times, 4 times?
I lost count.
Something like that.
Yeah.
We have some certain states that are numbered with a 1, or with an n. And we have two types of operators. We have the operator A, the annihilation operator, and we have an operation A dagger, the creation operator, or the hiring operator, the raising operator, however you want to call it. Then acting with A on this state is going to give the same state back, but minus 1. So it doesn't give the same state back, it gives a state lower than that back. And there is also some constant here. Similarly, acting with a dagger on your state is going to give a state back that is 1 higher than that. And also with some constant, a different constant. And if you recall correctly, this meant that our Hamiltonian, which was like a function of these Hamiltonian operator, which was a function of these creation annihilation operators. Let me not forget any heads.
All the hearts that aren't there are left implied, obviously. But yeah, if you recall that from specifically the second video, that was the big point, which is that we took our Hamiltonian, and Hamiltonian represents the total energy. We can only increase it by a certain integer value, or we could decrease it by a certain integer value. Well, not based on an integer value, not necessarily an integer value. The whole point there being that this means there are only certain allowed energy states you can have, nothing in between, which is per se quantization. And right now, it really seems like we have achieved something very similar, but this time with angular momentum, because we have our L plus, L minus.
Correct. And so I'm going to forego all the calculations they will be an exercise. But when you act with your L plus and your L minus on the AB states, what you do get is you get some constant and then the same state back, except your B is one lowered, or in this case one raised. And it's also not 1, it's 1 H bar. And similarly for your L minus, you are lowering an index in your state, once again the B, but now it is B minus H bar. So all in all, what you get is that your L plus and L minus operators, they are just hopping between levels of your B. Anything you want to add to that?
Not yet.
Okay, then let's make a small, well, let's say definition, transformation. I'm going to write some explicit, I have not written it down. Doesn't really matter. What I'm now going to do is I'm going to call my state slightly different. So I'm going to define A in terms of some L, and I'm going to define B in terms of some ML, which means that my state will become like this, the state of L and M of L. And the reason why I'm doing this is because in this notation, when you do all the definitions, your states become really easy to see. So in particular, the L squared operator acting on this LML state is going to be given by, from the top of my head, L plus 1 H bar LML, and similarly the LZ operator gives you H bar ML and then the same state back. And there is also one more thing you will find since these lowering and raising operators are changing the value of B, that means you can find some sort of minimum and you can also find a maximum. And using that maximum and minimum, you will find, is this still on camera?
Yeah, it is.
You will find that your ML value is going to be, there's only a couple allowed values for this one. It's going to be minus L is allowed, minus L plus 1, all the way to minus 1, 0, 1, all the way to L minus 1 and L. So these are all the allowed values for ML.
Yeah, and Hayek is actually right on the money here, because Hayek just said basically totally random choice of a name for variables, I guess, which, yeah, actually that is something that I would say is quite incredible about this, because in all the quantum mechanics, if you were lost, that first of all means that you haven't been paying attention in the past 4 videos which we've made, which is quite heartbreaking. We spent a lot of time and effort onto those videos. But second of all, that on itself isn't too bad, because what we've gotten at the end is ML and L, which you could recognize as the azimuthal and magnetic spin quantum number. My goodness, there's a horrible place to forget the name of the quantum number.
L is the azimuthal.
Yeah, L is the azimuthal.
And ML is the magnetic quantum number.
It's just magnetic.
Yes.
Which you could recognize as the reason, well, at least half of the reason why the periodic table looks the way it is. This right here is the reason derived from the very scratch. And if you look at the allowed values for L, even better, you can see that it starts at minus L, and then it keeps going through 0 till you reach L, which is precisely what you get. If you look at the periodic table, then it is not groups, because I always confuse the two. If only we had a chemist who could fill me in on the knowledge. It is obviously called the block. Then blocks are basically...
Do you want to show the blocks?
To get a group with this. I suppose I can. So, remember the fact, very crucially, remember the fact that when it comes to the L, right here, it goes from minus L through 0 to L. You don't know yet what the L actually is, but you will in a second. Now you drop it down. I can just move the periodic table right here.
Technology.
Technology indeed. And as you can see,
I need
we
to fix
start
this.
with just 2, which that I won't go into because ML. But then you can see every single different block is called differently, and we have the teal, we have the green, we have the purple, we have the blue, and they are respectively 2, 6, 10, and, well, if my quick maths, it should be 14, but I do not have the eyes to count them right now. And it is precisely for that reason. It's because for ML, you can have 2 values. And in this scenario, you start with L only at 0, then you start minus L, 0, plus L, then that's what gives you 6. Then you have 10, which gives you 5 possible values. So minus L half, 0, positive L half L, and then you keep going, etc., etc. And this is the actual, this right here, is the actual quantum mechanics that gives you this kind of structure of the periodic table. Obviously, the question on the left would be, why can you have different values of L, for which we would need to tackle the principal quantum number, etc., etc. Topic for another time, another stream. We'll get to that eventually, I promise. We need to model a hydrogen first, though, which is a bit of work.
Yes, so small recap again. We have constructed or quantified our quantumification. We have hadified our angular momentum, and we have rewritten the rules into such a way that we can create eigenstates depending on L and depending on ML, where we now also have 2 operators that move the ML up and down. It's, in a sense, it's very similar to the harmonic oscillator where you're jumping between the energy levels. Now, there is also a question of Timon I would like you to announce.
Which is the, I hope, why does commuting imply not measurable at the same time?
Yes, okay. I can answer that real quick. If they are not commuting, what we could do is we could consider, if they are not commuting and we have such a state, we could consider acting twice. So we could, for example, first act with Z, then act with total momentum on your wave function. This would give, you go away. This would give acting with Z would give you a B value. This would give a B value of this. And you know that this will give you an A value. If you do it the other way around, so you first do the total angular momentum, and then the Z momentum on your states, what you will get is total is A. You still have the Z left over on your state, and you can do that. Right, so, but real numbers commute, and which means that these 2 are equivalent or the same, which means that these 2 are the same, which is equivalent to saying they commute. So you cannot find such a state if they are not commuting. Gravity for another stream.
That's
So-
for special relativity, general relativity, doesn't matter.
Both.
Both.
So does that answer the question, first of all? And second of all, are there different questions?
No. Well, Flame says make sure you start with mechanochemistry, but like I don't see myself ever. I swear, making a stream about mechanochemistry is going to be one of the last things I do. That's ridiculous. Honestly, I genuinely, to everyone watching, I wish I could tell you just how much of a meme mechanochemistry is, but for that would require me to actually go to a lab of mechanochemistry, which is, I'm going on a tangent. I'm sorry. I just think
It's fine.
yeah. But questions I see none. Haig just said amazing, which I would say should give us confidence because Haig so far has been really understanding everything really well, which I
Thank
like.
you.
And no, I don't see any questions.
I guess we can then just simply continue. Because right now, our formalism, I haven't mentioned it, but I should have mentioned it. This angular momentum operator would work for a point particle. You could like act this, or all these operators, L squared, LZ, LX, L plus, L minus, you could act them all on a wave function or a state of a single point particle, which is crucial because of the following reason. In classical mechanics, which is exactly why I wrote this down, point particle only had orbital momentum. We are now going to quantum mechanics, and
well, there's no other way to say it.
there is no other way to say it. We're just going to give it spin.
Let's just assume. Remember the talk we had about how a point cannot spin? It doesn't make sense for a point to spin, because the whole idea of spin, if you have, let me just grab a random object on the desk, which is a pipe. If you have a pipe that's spinning, the whole point of the pipe spinning is that it's staying in the same place and only its features are rotating. So for example, this end of the pipe ends up right here. That's the whole point of spin. That's what spin is. Point doesn't have that. A point has nothing to spin, which is precisely why in classical mechanics it doesn't exist. But in quantum mechanics, our point particles are point particles because we observe them spinning.
They are found to be having a spin. This is done by measurements, Stern-Garlick, for example.
I cannot stress enough how that's it. There is...
It's Stern something. Gerlach. Mind my pronunciation. Sorry.
Blochsphere.
Blochsphere. So anyways, thanks for that, by the way. Right, spin. We are going to consider a point particle, a fermion, an electron, whatever you'd like. We are going to give it some sort of spin. Now, the nice thing is we have done all the preparation for this already. Because in classical mechanics, we showed that orbital spin, they are kind of the same thing.
Yes, we're going to use the fact that, once again, if we get back to the pipe, it's spinning on its own around an axis just gives you the spin, which doesn't make sense for a point. However, if you take the axis and if you move the pipe a bit away, then the pipe still spinning, this is still a spin, actually moves its position, which makes a tad bit more sense for a point, which is what we can use. That's all we have. We're basically grasping here a bit, but let's see if the maths work out.
Yes. So what we're going to do, we're going to start with our, I would say, most important equation, the way angular momentum commutes. This one. I'm writing big enough?
I would say I am blind and I have no idea. Everyone watching, also Timid has a follow-up to make sure they understand correctly.
We'll cover that in a second.
When we get to the net one, yes?
Yes. So this was our expression of how angular momentum commutes, orbital angular momentum operator, I should add. We can do the same. We're just going to say our spin angular momentum should act the same way. In particular, we have some operator x, sx, some operator sy, which is in the x direction, y direction, and this should give you the h bar spin operator in the z direction. This is this step simply follows from how similar spin and orbital angular momentum are in classical mechanics. So with these operators, we can do exactly the same thing as that we did for angular momentum. So in particular, we can define the total spin operator. We can calculate that it commutes with spin direction in the spin in the z direction. This is 0. We can create s plus and s minus, just like we did right here. Where am I going? I'm going to erase you guys. S plus will then be sx plus I sy, and S minus will the same thing with a minus sign. And from these we can, because this is commuting, that means we have some states. Let's go with S. Oh, fine, let's go with A and B. Not same A and B, let's go with C and D. We have some states, they will have something similar to this. We will find that our plus and minus on these states are acting again with adding an h bar or subtracting an h bar, which means I am still going to write this as ms. where these states jump the ms around with some prefactor. And we also have these two expressions similarly. Again, let me write them down. And set. And once again, your ms is going from minus s plus 1 all the way to s minus 1 and s. Now, there is one crucial difference with this. In terms of orbital angular momentum, the quantum version of it, so L, let's say L squared and Lz, in the case of L squared, your L can take any value. It depends on how much energy you give your system. If you give your system more energy, then your angular momentum will correspond to higher eigenvalues. But in spin, this is not the case. Because in spin, there is no such thing as, well, we're considering point particles. They are intrinsic. Even though we're giving them spin, there is no such, they can't spin faster in some way. They can't, there's nothing inside a point particle, which is the whole problem.
What would be the difference between a particle spinning at a certain speed versus double that speed? It's still a point at any second you measure.
So instead, this S is a intrinsic property of a particle. So to clarify that, let's for example consider an electron. For an electron, we would have a S equals 1, or S and half, not 1, thank God. S equal and half. That would be the case for an electron. For example, for, let's just say,
hypothetical non-electron.
No, I'm pretty sure one of these bosons, they have, well, of course, they're bosons. If you think, for example, of the mediator of weak force, or weak interaction, then this will have a spin of 1. If you think, for example, of particle I'm really trying to find, graviton, you'll find that it has a spin of 2. What this also means is, if you have a certain graviton, you know it has spin 2. But you also know immediately that the ms is restricted to all the values between s and minus s. So in particular for the electron, the only allowed ms would be a half or minus a half. For example, for the, let me write it a bit better. For example, for the boson, ms would be restricted to 1, 0, and minus 1. So there is 3 quantum states that describe your spin. In the electron, there is 2. In the case of the graviton, there is 5, I believe. Yes. So all in all, spin is an intrinsic property, or at least your S quantum number is an intrinsic property of your particle, which simplifies in contrast with your L, which could take not any, but it could take a lot of values.
It can just keep going forever, whilst spin only have 2 options.
Yes.
One or the other. And this actually goes even more interesting with if we consider what happens if we start applying this kind of system. Now, this part is very much not rigorous. I just want you to appreciate how much we actually went through here. Because effectively what we've gotten is 3 different values. We've gotten the L, ML, and the spin.
Yes.
Now, as we said, spin is an intrinsic property, which means for spin, the allowed values will not change. You will always have half and minus half. That much is simple. For the L, they can change because they range from minus L to L. And for the ML, they change.
Yes, but they are quantized.
But they are obviously all quantized.
Yes.
And so as such, I would like you to right now Once again, not quite as rigorous portion of the stream anymore, what I'm about to do, but still I would like you to imagine two things, if I may.
Oh, yes, of
Yes.
course.
I would like you to assume that there are two different rules that electrons would abide by. First of all, let's, you know what, I turned around and I've changed my mind. I don't think I'm going to be writing on the board.
You wanna have the screen?
I suppose I can just say it. Which is, first of all, I want you to assume that there is some kind of rule that the electrons follow. A rule that states that they cannot actually repeat quantum numbers. So if you have two electrons at the same spot, they cannot have the same quantum numbers. Let's call it some kind of principle of exclusion, some Paul's principle of exclusion, because first name that came to my mind. That's the first
It
one.
needs to be Italian.
It needs to be Italian.
Yeah,
It's like Pauli exclusion principle.
that's better.
Pauli?
Yeah.
Oh, that's crazy. Well, sure. We're making things up, might as well say. Pauli exclusion principle, why not? Then, second thing I would like you to assume is that there is some kind of fourth quantum number. We have three, right? L, ML, and spin. Let's say that there is a fourth one, and let's consider it to be the most important principle. Some kind of principle, the most important.
It's very important, yeah.
In that scenario, with those two together, we do have to realize that if we put a bunch of electrons into the same spot, they have to differ their quantum numbers. So first you would have a single electron with some kind of spin. Minus 1/2, doesn't matter. You chuck in another one, you would have two electrons with opposite spin this time, 1/2 minus half. Then if you chuck in a third one, well, it doesn't have an additional spin value to occupy, so it has to move on to the next quantum number, which will be ML. Then it will be L. And then it keeps filling, keeps filling, keeps filling. And then, once again, this thing that I've brought up before, that's basically the periodic table. That's basically the reason for the periodic table, the reason why it looks the way it looks. It's divided by the changes in principal, azimuthal, magnetic, and spin quantum numbers, which you don't often get such a direct link between doing quantum mechanics with abstract mathematics and operators and just visible chemistry.
Yes. If I might add something.
Yeah, go on.
So, in particular, to quick a recap of Make It Sad, you have the principal quantum number directly related to energy. You have your angular momentum directly related to total momentum operator. This is going to be hard to see.
Well, we are also saying it out loud, so it can be implied.
Yeah, but
I
like,
would say.
for the sake of clarification, where is the wiper? Yeah. I don't need the raising and lowering anyways. We have Hamiltonian gives you your n quantum number, your L squared, your total momentum operator, gives you your L quantum number, your LZ, in this case it could be any of the three directions, it gives you the ML quantum number, and your SZ proceeds to still write small. There we go. It's very important. And your S in some direction gives you the MS quantum number. So in particular, when you consider all these three states, and if this is sufficient, what you would have is you would have your particle or your function or your system be described by a wave function or a state, more specifically, that depends on these four numbers. And then using your operators, you could extract your eigenvalues, your specific energy, your specific angular momentum from this one state. And this is a big spoiler for the hydrogen atom, I suppose.
But to be fair, it's going to be a while from now.
Doesn't
I
matter.
think we're not going to cover hydrogen in a while. Any questions to everything that's on the board so far?
You said there was a follow-up question.
From Timon, yes.
Yes.
It just simply was, so they don't commute, and we calculate what we'd measure, we'd have two different solutions, which is not possible because we measure one thing. Am I understanding this correctly? Hold on, let me read that again. So they don't commute, and we calculate what we'd measure. We'd have two different solutions, which is not possible because we measure one thing. Am I understanding this correctly? I
think yes, but in case, I'll just add one more thing. This special vector, or in this case state, this is special in the sense that if you act with L squared on the state, you get an eigenvalue. If you act with Lz on the state, you get an eigenvalue. If these two are not commuting, so for example, Lx and Ly are not commuting, then there just doesn't exist such a special matrix. So in that case, you could still get your eigenvalues. You could still measure your system. For example, like this would be Lx, say, and your Ly would then be some different state, not the same one. That's crucial. You could still like measure this. Oh, this is Ly. This would be totally legal, but you would have to do extra care if you want to describe this eigenvalue in these kind of states, which is basically what we're doing with position and momentum. If you have position states and you want to see how the momentum operator acts, you get a special derivative, which in that case is a form of Fourier transform. I would suggest there is something similar right here. Maybe not Fourier transform, but there is you can write this in terms of this. So you get just a more complicated expression. And more importantly, this would not be an eigenvector or an eigenmatrix of that state anymore. That is, I guess, the crucial part. Hope that answers your question.
Good. Any more questions? Because now is the time to ask.
Before we go on with some applications.
Exactly. The theory, if you're confused about the theory, now is the time to ask. I don't think anyone is confused about the theory. Yep. No one seems to be confused about the theory.
Perfect. We're doing an excellent job.
Yeah.
Or no one is following.
Or we do such a terrible job that we can't even tell.
So, let's consider some applications. And I am going to only consider applications of spin, because that's the confusing thing. Angular momentum, sure, it's just, you can relate it back to classical. It's not important. Which means I need to be careful to leave all the spin on the board. You are not spin. Right.
I suppose Haig asked, does it link to the uncertainty principle? And yes, the commutation does link to the uncertainty principle.
Yes.
Considering how you asked the question, then I will say that you definitely know the answer. You just wanted to confirm, so I don't think we're going to explain it. Really good question once again. I really appreciate your questions. I'll try. I'm so lost. You're so lost, Avi. Well, we could really quickly recap what we did for the past hour and a half. All right.
Recap first.
I've
written it down.
Oh, you have? Well, then I suppose no recap.
No, recap first. We do a recap right now.
Oh, I was planning to speed run through this.
Oh, you can also do it if you want.
Well, I mean, I was going to do it simply and quickly. Basically, we have our states, which we covered last time. States contain the information about the particle, if you recall, but that information on its own is useless to us when it comes to observing things. That's just the information about our system. Then what we have is operators, which allow us to extract that information. For example, position operator and position state gives us position eigenvalue, position state, or in other words, operators are the things that we apply on the states to get the real values that we like. So for example, position, for example, momentum, for example, energy when taking off Hamiltonian operator, that's all we covered last time. This time we started with the angular momentum, so L, then we defined the angular momentum in classical mechanics. We also considered spin in classical mechanics, we move on to quantum mechanics. Here, the same principle applies, which is we have our angular momentum with hats, L hats. The only problem is that for reasons which would be a bit too much to condense for the sake of this recap, we cannot one does not simply use an L, and so instead we have the L squared. I'm doing it all without looking at the board because I am absolutely blind this, so you have to excuse me, I'm doing it from my head. We have our L squared, but most importantly, we got the L plus, L minus, which are like the raising and lowering operators. In other words, L, that's how you should think about it. L gives you the angular momentum value. L plus gives you the next possible angular momentum value, x minus gives you the previous angular momentum value. What happens in between? Nothing. You cannot achieve the values in between because it's quantized quantum mechanics. There we go. Then we considered spin. Spin is problematic because we're considering points, and points cannot spin. Why? Because they're points, but they can spin because quantum mechanics. I hope you're not confused by this so far. So then we took the spin, and with spin we ended up with certain possible values that aren't dependent on anything else. It's an intrinsic property. For example, for electrons, they can only have 1/2 minus 1/2. That's what else to mention. That can be quickly explained without going in depth into it.
I think that was a great recap.
For the rest, rewatch the stream and pay
You can
attention.
just rewind.
And watch the other videos. They have important context. Otherwise, you won't understand quantum mechanics.
Recap done. So, applications. Consider an electron. Gasp. It's a point particle. It does have spin, quantum spin associated with it. More particularly, we said before, it's a fermion. It has a half integer spin. In this case, electron has a spin of a half. What this means is that your states are given by a half, well, your S and MS states of this electron are given by a half MS, where MS could range from minus a half, or it could be a half. So, as you can already see, there is only two states that make this possible. We either have the state a half minus a half, and we have the state a half and a half. Second thing I would like to add is this half doesn't do anything anymore. I'm not going to write it down anymore. So in particularly, I'm just only going to look at the second part. Minus a half, and this is a half. Third thing, I don't like these halves. So I'm going to introduce a new notation. This one has a minus, so I'm going to draw an arrow to the minus. This one has, well, an implied plus. Must be looking up. So, our electron can be defined by two states. Either arrow up, arrow down, spin down, arrow up, spin up.
That's really dumb.
I know.
Because like the states are minus. I don't mean to be that guy, Remco, but I feel like that's not gonna catch on. I don't think people will start saying spin up and spin down.
Spin up,
Because
spin down.
Spin half makes sense. Spin up and spin down absolutely doesn't make
No.
any
The
sense.
spin half is the intrinsic property of the particle.
Yeah,
This is about the states.
no, spin half makes sense, is what I'm saying. But the thing you're doing with the up and down state, that one is not gonna catch on.
Oh, fine. We can also, if you'd like, you've maybe seen this notation. 0, spin down. In the case of spin up, we just do 1. Spin up.
Much nicer.
Happy, satisfied.
Much nicer, yeah.
So there's like 4 equivalent ways of denoting the same state. You could go crazy, write whatever. I think sometimes this is also, maybe it's more used instead of polarization, but like it still technically works. 2 different types of directions. Yay. This usually works for polarization. Anyways, the point is there is only 2 states. You have the plus and the minus state, spin up, spin down state. That makes the electron, at least when looking at spin, very, very easy. 2 possibilities. So let's make it a bit harder. Yes. Let's make it a bit harder. Or should we first do the funny thing where we just superposition? Or should we?
Should we just
Let's just mention it. So,
I guess.
quantum mechanics, the electron is either in a spin up or a spin down state. Now, this is the wrong one. Now, also quantum mechanics, it can be in both states at once. So if you have this arbitrary state of the particle, of the electron, would be given by some number times the spin up, plus some other number times the spin down. As long as these preserve probability, this is a valid state to describe your electron. It is now both in spin up and spin down. Next. two electrons, not at the same point or not around the same hydrogen atom, because then we get the Pauli principle exclusion principle.
Not asking because chemist, asking because Italian.
Yeah. And chemist, I suppose. Anyways, both of these have a spin a half. This one has spin a half, and this one has spin a half, which means both of them have ms equal to minus a half or plus a half, which means that now we can write the states a little bit easier. The first index of the state is going to represent the first electron. The second one is going to represent the second one. If you would like, you can also consider a tensor product between the two. This is entirely optional. Depends if you like mathematics or not. Would suggest you don't. I'm going to erase it. So the four different states are either both of them are spin up, and this would not be possible if they were in the same hydrogen shell level. Orbital, thank you. I don't do chemistry. The first one could be spin up. The second one could be spin down. The first one could be spin down. Second one could be spin up. And the fourth possible state, both of them are spin down. It was really easy to integrate spin up and spin down into this.
Yeah, it's really easy.
So now, with two particles, you have four possible states. And of course, if you want quantum mechanics, you can, I suppose, write an arbitrary state and let it depend on all of this. So some number A times both spin up, some number B, etc. You get the point. And in that case, both the electrons would be in some sort of superposition. But that is not enough. Two electrons is by far not enough. So let's consider. I don't have enough ink left in the pen. Let's consider n electrons, where n is really large. Or maybe not large. Consider some n. N is 461.
Not large.
Oh, you thought?
Whoa, I got owned. Okay, well.
Anyways, now, once again, there is different. Each of these electrons have a intrinsic spin half. They have two possible states with them. So in effect, you could just have the state all up. You could have the state, the first one down, everything else up. As you might see, I'm not going to write all of these down. The principle is just by combining different electrons, as long as they're not in the same location, you can just basically enlarge your states, add them all into one big state. And, well, it's a very convenient way of describing spin of electrons, I would say.
I would say so as well. Chris also is asking, because this is so suspicious, whenever a physicist says, because this is impossible, they are omitting something. So is it possible to force electrons to have the same spin? Or is there some really fundamental reason they can't be? That's the question.
I know.
We'll get back to you on that one.
How about tomorrow?
Well,
okay, no, it should be actually impossible because it is forbidden. But I don't recall from the top of my head why it is forbidden. The moment I have, I will share, I suppose. Oh. That's a really good question. It's great to be suspicious of us.
like Pauli we can explain. That one we can.
I mean, you for sure need the spin statistic theorem. But I don't feel like deriving that on spot.
This will definitely be something for a video rather than a stream.
Well, here you hear it. There is a promise now that it's going to be in a video.
Yeah, congratulations.
You talked yourself into that.
Oh.
Good job.
I'm gonna.
My job here is done. Any other questions?
And don't be careful with the questions. Questions may lead to videos. Is intrinsic? That's why it is forbidden, I guess.
No, because what you're talking about is not your S. The S is intrinsic. You're talking about your MS. So basically, what you would be wanting is a hydrogen atom, a proton, whatever, 2 electrons in the first orbital. This is an electron. This is an electron. And what you would want to describe them, you would want to describe them with the first electron has this state, spin up, and the second has exactly the same state, spin up.
Yeah, but this can't happen because of Pauli, no?
Yeah, exactly. This is the, like, you're not talking about your S, you're talking about your MS. This would be forbidden, which is there needs to be a minus here, which is why the orbitals don't fill up. But
yeah,
deriving the Pauli principle is.
I mean, he has an easy intuition. Yeah, sure. Well, I mean, we're gonna have to go on a bit of a tangent, I suppose, and I kind of feel like the other board would be fine for this. So basically, category theory. There is a morphism between vectors and functions.
Oh, yep, Timon is right.
What is it?
It's an argument on the wave function. The wave function needs to be antisymmetric. So
Yeah,
if you
that's
swap
literally what I was about to write. That's why I
Proceed.
started. That's why I started the morphism between vectors. Fine. No, I want. No, it's fine. Whatever. It's really neat graphically because you can show that the absolute value of a wave function looks the exact same, but the actual value of the wave function, when you don't take the absolute, is actually the opposite. Which means if you swap them around, it's different. Whatever. I won't do it. Why do I ever bother?
I invite you to implore this on the whiteboard.
It would. We have not covered wave functions at all, though.
No, that's correct.
Which I suppose we should first cover the wave functions.
But it is a question, so from a specific person, so you can, like this is not general knowledge.
I'm not certain if I'm going to draw it properly on the first spot, but basically you can imagine it like this. There we go. If you take an absolute square, this is your 0 line. The marker is dying. So you can see that you can just visualize in your head because the marker is dying, which is that if you have this, if you swap the two of them around, they will be different because then you will have first up peak, then down peak, first down peak, then out peak. So if you swap them around, that is very much different information. However, the absolute value squared is the same, which means that you cannot just freely swap them. Yeah. It leads to just something completely different.
Yes.
Which is why you need why you need them to be different no matter what.
Yes, I suppose.
Category theory mentioned. That's how I'm gonna start. That's how we're gonna start explaining the wave function, by the way. First step, there is a morphism between vectors and functions.
Oh no.
I actually don't know if there is a morphism between vectors and functions. I'm guessing.
The wave function is a inner product with one spot unfilled.
Yeah, but is there actually a morphism between vectors and because there might not be. There might be more vectors than it is. No, there might be a morphism between vectors and functions.
Maybe, but maybe ask Lycan.
I need to ask the mathematicians. This question segment isn't going really well because we ended up with the questions, so that's this is not going great.
Is there any other questions?
Not yet. Oh no, Timon mentioned. No, Timon mentioned. Isn't that an electron and a positron interaction? What Timon mentioned? Because that looks like annihilation.
No, the wave function is antisymmetric, which means if you swap two components in your wave function,
yeah,
two indices that correspond to electron 1, electron 2, you should get a minus sign. But since they are the same state, if you swap them, nothing happens, which means you get your wave function equals minus your wave function, so your wave function is 0, which means it's not feasible.
Yeah.
I can write it out real quick, but
no, I cannot. No.
But the it has nothing to do with pair creation, no.
I see the confusion though. Good question.
I suppose.
Isn't it true that they do pop in and out? We will tackle the Dirac Sea another time.
Ooh, but I like swimming in the Dirac Sea.
It is fun. Oh my goodness, Dirac Sea actually comes from E squared.
Yes.
Oh, that's comical. That is really comical. You know, we should really cover special relativity at some point.
I would say that's a great idea.
Yeah.
I suppose there is one more application / preview I can give to as a final remark.
Mm-hmm.
Well, I would like to pencil them. If there is no more questions, that is.
I don't. Well, Leo is questioning the Dutch, but I don't think that's something we.
I mean, I also question the Dutch, don't worry. It's a totally normal thing to do. Happy. There. I guess I can reflect back to the beginning of the stream when someone mentioned something coupling.
Why the pipe so small? That's not a small pipe. What do you mean? That's completely average. Have a pipe for comparison.
I would say
Here, have a pipe for scale. That's a completely normal pipe. And in case you can't like scale it properly, have a pipe for scale.
I think I do have some other pipes for scale.
Like, hold on. Do we have a bigger pipe? This feels plenty large for a pipe. One of these has to be bigger, right? Well,
No,
actually, no. They're all the same size.
I think this is the biggest one. This one is also big.
Yeah, that's true.
But these are equal.
But these are mine, so.
I would say it is a really big pen. Anyways, final application then, if there is no more questions. What you could do is you could consider all these electrons, but now you put them in some, suppose, lattice. And funny things. But all of these are electrons, all of them have spin half, which means they all of them either have a spin up state, spin down state, spin up state, up, down, doesn't really matter which configuration exactly. What you could do is you could write down a Hamiltonian talking about this, talking about how the spin talk to each other, and with that you can do a lot of stuff. It's a possible way you can go. I'm not going into the details, but you could couple the electrons to each other through interaction strengths, and etc. etc. And you get funny results for another time.
For another time, indeed. Well then, there are no more questions. We will cover this all eventually in videos, plural, because there is a lot of build-up, and we will actually cover even more. One thing which we have omitted, which I am a bit heartbroken by, is the generalized commutator for the angular momentum operator, because we have the angular momentum operator.
Fine.
So you don't have to note it down. The reason why it's really neat is because it does actually include the change of sign. It depends on which direction you go in for the commutator itself. If you go x, y, z, you get a negative, if I'm doing it correctly from memory. If you go z, y, x, you get a positive. Which those among you who are interested in this sort of thing, you may notice this actually mimics the commutative properties of quaternions, which they themselves mimic the commutative properties of Pauli matrices, which are really good to describe spin on a Bloch sphere. All of those will be coming in videos that will be made. But for now, all I'm going to say is do the exercise. There is an exercise available on the website, and there is a video associated with that gives you the link. So go ahead and do the exercise. It's really fun. It will give you an advance in quantum mechanics, and I think that'll be it. Thank you so much for watching, and have a great day.
Bye.